Hey everyone! Welcome to part 2 of the PID line follower robot build series. In the previous video, I have shown how to assemble the complete hardware kit for the robot. Now, in this part, we're diving into the coding side. I'll guide you step by step on how to read and process sensor values using Arduino Code. Quick look at what's inside the kit. You'll receive a line follower chassis, a custom-designed PCB carrier board, gear motors, 3D printed wheels with grips, an 8-channel analog IR sensor array, an N20 ball caster, a rechargeable battery with a holder, connection wires, screws, and everything you need to assemble your robot. The kit even includes a preloaded operating system with an OLED display and a demo line following code, so you're ready to test and run your robot straight away. If you're interested in purchasing this kit, feel free to message us on our Facebook or Instagram page of Robotech Innovator. If you're new here, don't forget to hit the subscribe button and turn on the notification bell so you never miss any of my upcoming videos. This video is sponsored by JLCPCB. JLCPCB provides easy, affordable, and reliable PCB and PCBA solutions. For this project, I designed my PCB using EasyEDA and exported the Gerber files. Then, I created a new account on JLCPCB and received a total of $60 as a welcome gift for new users. To place my order, I simply uploaded the Gerber file to their website, selected the quantity and color options, and finalized the order. You can get 5 high-quality PCBs for just $2. What's more impressive is that JLCPCB provides real-time tracking of the entire production process, so you know exactly what stage your order is in. After a few days, the PCBs arrived at my doorstep. Then I assembled the board with the required component. Then I tested PCB and everything worked perfectly. If you're looking for a smooth, affordable, and professional PCB manufacturing experience, JLCPCB is the way to go. Here, I'm using an Arduino Nano along with a 16-channel analog multiplexer to read data from multiple IR sensors. The multiplexer allows the Arduino to read up to 16 analog signals using a single analog input pin. This is essential when we have more sensors than available analog pins on the Nano. Let's begin the coding process. First, I opened the Arduino IDE and created a new tab specifically for writing the sensor reading section of the code. To start, I wrote a function called selectChannel. This function activates a specific channel of the multiplexer, allowing me to read from individual sensors. Next, I created a function named readBlackLine for my line follower robot. Inside this function, I used a for loop to iterate through all the sensors connected via the multiplexer. For each sensor, I called the selectChannel function to enable the corresponding channel on the multiplexer. A short delay is added after each selection to ensure signal stability. Then, I read the analog value from the currently active sensor and stored it in an array named sensor ADC. Let's assume the variable sensor number holds the total number of IR sensors used. So, defining the array sensor ADC at the beginning of the code. At the top of the code, I defined the multiplexer control pins and set them as output within the setup function. To help with debugging and visualizing sensor data, I printed the analog values of each sensor side by side using the serial print function. Next, I incorporated a push button into the program by defining a pin named button1 pin. In the setup function, I configured this pin as an input with the internal pull-up resistor enabled. This means it will read as 1 when the button is not pressed, and 0 when pressed. Inside the loop function, I added a condition to check if the button is pressed. If it is, the readBlackLine function is called, and the analog values are printed to the serial monitor. I also made a small correction in the serial print formatting for better readability. After finalizing the code, I uploaded it to the Arduino board. Then, I opened the serial monitor and pressed button 1 to start the program. As expected, the analog values from the 8-sensor IR array appeared on the serial monitor. On a white surface, the values are typically below 100, while on a black surface, they are generally above 900. However, keep in mind that these maximum values may vary depending on the specific track or lighting conditions. Next, I mapped the analog sensor values to a range from 0 to 1000 for better consistency. If a sensor reading is less than 200, I treat it as the minimum and set it to 0. Conversely, if the analog value is greater than 300, I treat it as the maximum and set it to 1000. After implementing this mapping logic, I uploaded the updated code to the Arduino. Once again, I opened the serial monitor to view the sensor readings. Now, the sensor value processing is much more accurate and efficient, making it easier to distinguish between black and white surfaces. Now, I'm adding logic to convert the analog sensor values into digital format. If a sensor value is greater than the threshold, I consider it as 1, indicating the presence of a black surface. If the value is below the threshold, I treat it as 0, indicating a white surface. To implement this, I defined an integer variable named threshold and assigned it a value of 500, which lies between the typical minimum and maximum analog values. After writing this logic, I uploaded the code to the Arduino once again. Opening the serial monitor now shows the digital representation of each sensor. This digital conversion significantly improves the clarity and efficiency of the sensor value reading system. Now, let's understand how the sum of sensor values is calculated. The sum on sensor refers to the total number of sensors currently detecting the black line. It is simply the summation of all the digital values in the sensor array. For example, if the sensor pattern is 000111000, then the sum is 2, meaning 2 sensors are currently detecting the black line. This sum helps us understand how many sensors are actively on the black line at any given moment. If all sensors detect white, the sum will be 0, and if all sensors detect black, the sum will be 8. This value plays a key role in determining how centered the robot is on the line. So now I'm going to incorporate the equation to calculate the sum of active sensors. Then, I'm declaring an integer variable called sumOnSensor at the beginning of the function to store that value. Each sensor in the array is assigned a specific weight value to indicate its position relative to the center of the robot. These weight values help determine which side of the sensor array is currently detecting the black line and how far the robot has deviated from the center. Using this information, we calculate the positional error of the robot. The weight assigned to each sensor is predefined and usually increases from left to right across the array. This allows us to quantify the line's position relative to the robot's center. In this example, the weight values for each sensor are displayed, along with a sample calculation based on the digital sensor values when the robot is perfectly centered on the line. The resulting weighted average gives a value of 90, indicating a centered position. Next, I'll write the code to calculate the sensor weight. Now, I'm defining a weight value array which contains the weight values for each sensor, for example, 10, 20, 30 up to 80 for 8 sensors. These values help us calculate the line's position more precisely. Now, let's understand how bit sensor conversion works for an 8-sensor array. To represent all 8 sensor readings as a single number, we assign each sensor a unique bit weight of 1, 2, 4, 8, 16, 32, 64, 128, from the first to the last sensor. For example, if the sensor values are 10110001, it means sensors 0, 2, 3, and 7 are active. Now, by multiplying each sensor's value by its bit weight and summing them up, so, the final result is 141. This number holds the same information as the 8 digital readings, but compacted into a single variable. After that, I'm adding the equation to calculate the bit sensor value, similar to how we calculated sensor weight. I multiply the digital value of each sensor with a bit weight array. Again, only active sensors will be counted. I'm also defining the bit weight array, which contains values like 1, 2, 4, 8, all the way up to 128. These are powers of 2, used to convert sensor states into a binary number. I also declare a variable bit sensor to store this result. Now I'm updating the serial print function to show everything clearly in the serial monitor. You'll see the 1s and 0s for each sensor, followed by the total number of active sensors, the calculated sensor weight, and the bit sensor value in decimal. As the robot moves and different sensors go over the black line, you'll notice the values change in real time. If it's shifted to the left, the right side sensors are active, so the weight value increases. When the robot is shifted to the right, the left sensors become active and the weight value decreases. The bit sensor variable used in this code holds a decimal value by default. To view or work with its 8-bit binary representation, we can use the bit read function, which allows us to read individual bits from the decimal value. Alternatively, we can directly assign a binary value to the variable using the 0b prefix. You'll also notice that the bit sensor value changes. You can view it in both binary and decimal. This is very useful for debugging and also for writing pattern-based line-following logic later. Try observing what happens when all the sensors are on white. The values drop to 0. And when all are on black, you'll get the maximum weight and bit sensor values, which is 255. These patterns are important and we'll use them in our line-following algorithm. That's it for the sensor reading part. In the next part of this video, I'll be explaining the motor control logic. So, stay tuned, and don't miss the next video to watch.